So our speaker today is Lena Collienne, and Lena is a PhD student here at the University at Otago in New Zealand, and she is involved in exciting work on computing the nearest neighbor interchange distance between trees, but she's looking at ranked trees. So she's working in the ranked world, so to say. And today she will be talking about some new results. So please, Lena, go ahead with your talk.
Thank you. I'm going to talk about the complexity of computing distances between ranked trees and these distances based on the nearest neighbor interchange operations. But before I talk about this, I want to talk a bit about the biological motivation, because I sometimes tend to forget that it's there, and there's a reason we do all this, and so I briefly want to talk about that. So first of all, the first question is, why do we consider ranked trees? Why are they important? So one motivation is coming from cancer, because in cancer phylogenes, it matters that the ranking or the order in which internal nodes appear matters. So for example, if we have this is just a toy example that I made up. If we have trees on a sample from a metastasis of a tumor, and the main tumor was in the pancreas, so it has the letter P, then there is a metastasis in the lung and 2 in the brain. And we have these 2 trees, then these trees are topologically the same, but the ranking is different. And that's why it tells a different story. So here you can see that on the left, first we have a metastasis growing in the lung, and then later on one comes to the brain, or metastasis starts growing in the brain. But on the right, it's the other way around. First there's one in the brain and then the one in the lung. And this is important information if you want a treatment, for example. So the question of the ranking of the tree is important in this case. Another case, which is currently very important, is in epidemiology. When did transmission events occur? So for example, when a virus gets transmitted, when did it happen, and which event happened before another event, which is, for example, in New Zealand, interesting to know if the transmission happened inside New Zealand or while people were still overseas or so. So this is why we want ranked trees. And why do we want distances between trees? Well, one thing is, if you infer trees from data, you might get different trees through different methods. So this is, for example, a tree that Jirka, the postdoc in our group, created on, I think, the same data set, but with different methods, and he got 2 different trees. I don't know how correct they are biologically and what exactly they are made from, which kind of data, but it's different methods, same data. And why do these trees, how similar are these trees now? That was the question that he came up to with me, for me, and I was thinking, yeah, well, we need a reasonable distance. Well, the easiest is probably Robinson folds. Others are hard to compute. But it would be nice to have a measure of how similar trees are. And another interesting thing that we could do if we have distances that we can compute efficiently is, if we have a sample of trees, can we summarize it, or can we find a mean tree for the sample? And a meaningful mean tree. Some distances have the problem that you get a star tree as a mean tree, which is not so helpful. If you, for example, want to summarize the posterior distribution you get when you run a Bayesian or use a Bayesian approach to infer trees. So for summarizing trees would also be nice to have distances. So that's why we want distances for ranked trees. Yeah, the way we want to do it is we want to, I will define a graph on trees. So the nodes in this graph will be trees, and there will be edges between trees if they are somehow similar. And the somehow similar, there are already some different measures for that. And these are the tree rearrangement operations. Most commonly are RNNI, SPR, and TBR. And so if we can get from one tree to another with such a tree rearrangement operation, then we would draw an edge between these 2 trees. And so each of these tree rearrangement operations would give us a graph on trees. And before I start talking about ranked trees, I want to talk about NNI, because NNI is what we focus on here, later on ranked trees, but for now, we will just consider rooted binary trees, and for now forgot the ranking. So I always now assume every time I say tree, I actually mean a rooted binary phylogenetic tree on n leaves. In this case, n is 8. So, and NNI moves on rooted trees, the first time I saw that, I was a bit confused because it's usually NNI moves are defined on unrooted trees. So it looks a bit different in rooted trees, but it's actually exactly the same. So there are two different definitions that work for rooted trees. The first of which is the following. So we have here NNI neighbors, 3 trees that are NNI neighbors, and the NNI move happens on this dashed edge. So how do we get from one tree to the other? Let's consider the tree in the top left, and we can get to the tree on the right by cutting the edge of which is below the top node of the edge on which we want to make the move, and then connect it to one of the children of the lower node of this edge. So in this case, we cut the edge leading to the subtree B, and then we connect the subtree B to C. And this gives us the tree on the right, which here looks a bit awkward with the edge, but it is this tree where B and C now are here in the cherry, and then D is up here. And the same way, or similar way, we can get to the tree on the bottom from the tree on the left. We cut it the same, we cut the same edge, but then we attach it to the other child here, so to D. And then we get the tree, which looks like this, but if we resolve it and draw it more beautifully, then we have this cherry B and D, these subtrees here, and then C on the other side of the edge. And these trees correspond to the unrooted NNI neighbors the following way. So you can, if we draw these trees as unrooted trees, there's an NNI move on the edge there, which is probably the more commonly known version to draw it. And actually the NNI space for rooted trees is the same as for unrooted trees. It really it's not the same, but it doesn't matter where you put the edge if you want to compute the distance between two trees. The distance is the same no matter whether there's a root or not. So this is the first definition. The second definition, which I think works better for rooted trees, is the following. So we say that two trees are NNI neighbors if they both contain an edge, such that shrinking this edge to a single node results in an isomorphic tree. So in this case, if we shrink the dashed edge in each of these trees, we will get this tree, which is not a binary tree anymore, but for each of these 3 trees, we get this tree. So you can also see an NNI move as shrinking an edge and then popping it up again at another place. So these are the 2 ways how you can see NNI moves in the case of rooted trees. And this now gives us a tree space on this on phylogenetic trees, and the edges are given by these NNI moves. And now the question is, can we compute distances between these trees in this graph? So we have given a pair of trees, T and R, and the problem is give me the distance in this graph. This problem is known to be NP hard. That has been proven, and I think it took like 25 years or so to prove it. It took quite a while. This problem was known for a while, and there were also some wrong attempts of proofs, but finally they made it, and it is NP hard. There is a fixed parameter tractable algorithm, but I think all of these tree rearrangement operations, which are commonly known, this always depends on the distance. So as long as 2 trees are close to each other, we can compute the distance efficiently. But if they're further away from each other, it's not tractable anymore. There is an approximation algorithm that I found. There might be better ones, I'm not sure. But the ratio was O of log n. The diameter of the space is n log n. So this is, can be useful sometimes, but in general, that's not good news. We can't compute the distance, especially for big trees and if they are far away from each other. So that's not good. We want something better than that. Another interesting property that NNI has, which is biologically not so great, is that it does not have the cluster property. What does that mean? For example, consider these 2 trees, T and R. They both consist of 2 caterpillar trees, which are here represented by these dotted lines. I was too lazy to draw more. So on the left side of each of these trees, we have the leaf set, the leaf labels from 1 to n. So on this side, and T on the left, we have 1 to n, and with the dots here, I wanted to say that also these leaves are 1 to n, the same as on this tree. And on the right, we have the leaves in n plus 1 to 2n, and here also these leaves labels will be in the set n plus 1 to 2, and they will just be permutations of these. So this means that these two trees share two clusters, because this cluster, the leaves from 1 to n, are in the tree T, and this cluster also appears in R, and same for the cluster on the right. So they are the same. So now you would think it would be reasonable if on the shortest path, you would keep these clusters in every tree on this path. So you just sort things in these two subtrees separately. However, what happens in NNI if you choose the trees correctly in the permutation is that you merge the two clusters and build lots of cherries where every cherry contains an element of one subtree and of the other. Then you sort these cherries separately. So these three actually are not the same. So the cherries are built here, then these cherries are all sorted, now they're in different order here, and then they get split up again to these two subtrees with the caterpillar trees, which have the clusters. And actually, as has been shown, that the examples where there's no shortest path, where these two clusters are actually maintained on the shortest path. So that is, from a biological point of view, not ideal, to be honest. So that's, and it is actually believed to be related to the fact that computing the NNI distance is NP hard. So that's something that we should, that we want to keep in mind. I will come back to that later. Another thing that is, depending on the application, relevant is that NNI move is probably not equal to an NNI move. What I mean with that is that if we, for example, do an NNI move on the tree on the left here, on this dotted edge down here, it just swaps the order of two leaves here, A3 and A4. But it seems like it's not a big change to the tree. But an NNI move on this edge changes this cherry to be, see these two separate leaves, and we end up in a caterpillar tree. And depending on the application, these two moves are actually very, very different. And if you assume that the branch lengths say something like, for example, time, then you don't want these two moves to have equal weight, because it's a more drastic change to change this cherry into these two separate leaves here. So what we now want to do is we want to rank this tree to make sure that these two moves don't count the same number. There's just one move. We want to have a bit more than one move for this huge change of resolving the cherry. And for that, we consider ranked trees. So in these ranked trees, we always assume that the leaves all have rank 0, so we consider ultrametric trees. And then we have the integers from 1 to n-1, which are the ranks of the internal nodes. And the only rule we really need to follow is that a parent always has to rank greater than their children. So this can give us, for example, the order in time of where these divergence events in the tree happens. So this is now what we want to consider, and we want to consider NNI on these trees, NNIs on ranked trees. And let's go back to the example I had before where we resolved this cherry. So what we want to do, we want to make this move count more than 1. In plain NNI, it's just 1, but we want to be more expensive. So therefore, we first rank the trees. So we now assume that this cherry A7, A8 has rank 1, the internal node of this cherry, and then the other ones have the ranks 2 to 7. And we introduce a new move. And this move we will call a rank move, and we give this move a weight. This weight is rho. So the rank move simply changes the ranks of two nodes if they have rank difference 1. So it can change the rank of 1 and 2 here, and then we end up in this tree. And now we do this 4 more times and move by that the internal node here up and exchange it with every internal node here. So we have 4 rank swaps. And then we now have an edge of length 1, and we allow NNI moves on such an edge. So NNI moves in this space for unranked trees are only allowed on edges of length 1. And by adding the rank moves and this weight for the rank move, we have now the distance from this tree on the top left to the tree on the bottom left. This is now 1 plus 5 rho, and before it was just 1 in plain NNI. So we made the NNI move a bit more extensive for these ranked trees. And with this, we get a new tree space, which we call RNNI of rho, because it depends on the parameter rho that we choose as weight for the rank moves. And now this tree space has a set of trees, ranked trees, and we have edges for rank moves. For example, the rank move here exchanges the ranks of these internal nodes marked by a dot, and we have NNI moves on the dashed edge, for example, here, and the NNI moves we weigh by 1 and rank moves by rho. And depending on your on what you want, you can choose this rho to be anything. It can be anything between, I would assume it should probably be positive, between 0 and infinity. So now we want to again consider the distance problem, but not only the distance problem, we want to make it a bit more complicated, and we actually consider the shortest path problem. So in the shortest path problem, we assume that we have given a pair of trees T and R and want to find a path of minimal weight between these trees in the space RNNI of rho. So path of minimal weight, so we sum up all the weights on the path. So that will be, for example, before it was 1 plus 5 rho for our example. So what do we know about this problem? First of all, if you choose the parameter rho to be 0, this problem is NP hard. And this is this follows quite easily from the fact that computing distances or shortest path in NNI is NP hard as well. Because if we have the rank moves weigh 0, for example, as we saw before, if we set rho here to 0 in that example, then we can go from one tree to another tree for free if they just differ by the ranking of the nodes. So we only need to do one NNI move and everything else weighs 0. So this is again from this tree to this is NNI. This is the distance in RNNI of 0 is actually the NNI distance. So what we want, and if we want to compute the shortest path in RNNI of 0, is we want to minimize the number of NNI moves. So we want the shortest NNI path, and that is NP hard. So computing the shortest path here is NP hard as well. But now what happens if we set rho to the next obvious value that's possible? What if rho equals 1? Well, we get this space. So we have, this is not the full space, obviously, but we set the rank moves to be weight as 1, but then as well we can just, because every edge in the space will now have the weight 1, we can also consider the unweighted graph. And for this graph, I want to show you an algorithm to compute paths, because yeah, we found a way to compute paths between arbitrary trees in this tree space, which we only call RNNI. So we leave out the 1 and just say RNNI here, because yeah, we don't consider weight on edges. So this algorithm I called find path because I'm very creative and I didn't find a better name. And this algorithm is a greedy algorithm to approximate this problem, to approximate shortest path in this graph RNNI, or RNNI of 1. It has quadratic running time, and we could computationally show that it computes shortest path for up to 7 leaves, because we can actually compute the RNNI graph for up to 7 leaves. Everything else is too big. That's not feasible anymore, but we can prove that it's actually computes shortest path, not just any path, but shortest path. And I want to show you how this algorithm works with an example, because you'll see it's a very easy algorithm. So if we have giving 2 trees, T and R, T in this case is a caterpillar tree, where the leaves are labeled from A1 to A6. And in R we have 2 cherries, one here is A1, A4, then we have another one, A3, A5, and then A2 and A6 for here. What we do now is we consider the internal nodes of R from bottom to top. So we start at the lowest internal node of R, which is marked in blue here, and it has the children A1 and A4. And then we look for the most recent common ancestor of these 2 guys in T. So the most recent common ancestor of A1 and A4 in T will be this node in blue here. And now we want to move this down. We want to make sure that we end up with a tree that has this internal node of R. So we do an NNI move, and the first case here, to exchange A3 and A4, and by that we move the most recent common ancestor of A1 and A4 down by 1. And we can do this again and do an NNI move that swaps A2 and A4, and then we have this internal node down here, and this is exactly where we want it to be in R. So we have the first internal node of R solved. Great. Let's go on to the next one. And this one has A3 and A5 as leaves descending from this node. So we consider now the most recent common ancestor of A3 and A5 in this tree, and we find it's there. And we do the same thing again as before. We now move this most recent common ancestor down. So first move that will happen is an NNI move that builds a cherry. Now the most recent common ancestor is one down. And then we do a rank swap. And we end up here. And this tree has this node the same way that R has it. And then we go to the next internal node of R, which is this black one. And the leaves descending from it are A1, A4, A3, and A5. So we look for the most recent common ancestor of these 4 guys in this tree. And we find out it's this one. And we move this down. And we just need to do an NNI move to do that. And then we already end up at the tree R. It could be that the trees are still not the same, so then we would need to consider the next internal node of R as well. So you basically just go through all internal nodes of R, and then you move most recent common ancestors down in the current tree of our path. So yeah, it's a greedy algorithm. It's quite simple approach. And now a cool thing that we found out about this algorithm, which I'm very excited about, is that it actually computes shortest paths. So for quite a while, we were thinking that it at least approximates shortest paths, but we found out it actually computes shortest paths. And actually what I didn't say before is that these moves to move the most recent common ancestors down, they are unique. There's always exactly one NNI move, so one rank move or NNI move that moves this most recent common ancestor down. So it's definitely, so it's a deterministic algorithm, and in the end, it actually computes shortest paths on RNNI. The proof for that is, to be honest, not the most beautiful one, but it works. And I just want to tell you the idea, because the idea is nice. How it's done in the end is not so beautiful, but there are heaps of cases. That's basically the gist of it. So for the proof, we used, to tell you how the proof works, I want to use the notation FP of TR, and this will be the path between TR that find path computes. So this is a sequence of trees, the path. And we use the following lemma to prove this theorem. And this lemma says that if we have 2 trees, T and R, and we want to compute the distance between them, then if we take the path that find path computes between these 2 guys, and we consider neighbor T prime of T, then the distance between this neighbor of T and R cannot be smaller than the distance between T and R minus 1. So it must be greater than that. And if this is true, then the length of find path actually is the distance. So I have a small figure to explain that, so it's probably easier to see then. So we have this tree T here and R here. And we prove that for a neighbor T prime, so this is a neighbor, we draw an edge here now. So this tree T prime cannot be closer to R by more than 1 move than T is to R. So if the distance between T, or the path that find path computes between T prime and R was two moves shorter than the one between T and R, then then the length of this path could not be the distance. That's basically it. And so we only need to prove this inequality. And we do that by looking at what kind of moves could happen between T and T prime. So there could be a rank move, there could be an NNI move. And then we consider the start of, then we consider what happens on the path computed by this algorithm find path. And we distinguish between what kind of move happens here between T and T1 on this path from find path, and between T prime and T1 prime. And there are heaps of cases because different things can happen, different moves can happen, and we need to compare all of those. But in the end, it turns out that we get shortest path by this algorithm in this space of ranked trees, which is very nice. Yeah, so we found out that we can compute shortest paths here, so this seems to be an interesting space. So let's take a look at the geometry and some properties of this graph. First of all, the number of ranked trees is n factorial times n minus 1 factorial over 2 to the n minus 1. Then an interesting thing is the diameter is quadratic. It's so it's n minus 1 choose 2 or n minus 1 times n minus 2 over 2. This actually shows us that if we want to compute shortest paths, we can't do better than find path, because find path has complexity n square. So and shortest path can get that long. So if we want the shortest to compute the shortest path, we can't do better. We can't get a better running time than find path, which is also good to know. What is also interesting is that not only the diameter is quadratic, actually the radius of the graph are the same as the diameter here, which basically means that for any tree for any ranked tree, we can find another ranked tree that has maximum distance from it. So the distance between that and the other tree would be the diameter, which is an interesting property, which basically says something like most of the trees have maximum distance from each other or close to that. Yeah, and another thing is the cluster property. I talked previously about it in NNI. Told you NNI does not have the cluster property. On shortest paths, these clusters are broken. If we again consider these trees that share a cluster, or any trees that share a cluster, what find path does, it would just move these most recent common ancestors down, and it would do that on either side of these trees. And it would never happen that something moves across the edges which are connected to the root here. So the clusters are actually maintained on the paths computed by find path. But there are other shortest paths. So the shortest path in RNNI are not unique, but we can actually show that every shortest path, if there are two clusters shared between two trees, then every shortest path has this cluster in every tree. So RNNI does have the cluster property, which is quite nice. Then another thing is caterpillar trees. That is actually where I started with in the beginning when I considered RNNI. We could prove that the set of caterpillar trees is convex. What does that mean? That means that if we have two caterpillar trees, there's always a shortest path between them that only consists of caterpillar trees. So if we, for example, have these two trees, here we have A1 to A5, and here we have a cherry A4, A5, and then A1, A2, A3. Then the path that find path computes is actually this one, where we first build this cherry A4, A5 because it's the lowest node here. And then we move it down by some rank moves until it's here. Then we resolve basically this part of the tree by doing two NNI moves and end up in this tree. And there's the length of this shortest path is 5. But on the other side, there's actually shortest path, which only consists of caterpillar trees, where you first move down the leaf labeled by A4. You take just two NNI moves, swap it first with A3 and then with A2. We end up in this tree, and then you move A5 down by swapping it with A3, A2, and then A1. So there's also caterpillar paths. So even though find path does not compute trees only consisting of caterpillar trees between two caterpillars, there's always a path that only has caterpillar trees between them. We could also prove that. This is not true in NNI, by the way. So that's also a difference between this ranked NNI and the plain NNI when we don't consider rankings. So there are quite some interesting properties of the space. So back to the complexity of computing shortest paths. So we saw for RNNI of 0, it's NP hard because it is basically NNI. For rho equals 1, for RNNI of 1, it can be solved in quadratic time. But I introduced this parameter and didn't say anything about other values yet. So what happens for this parameter rho, the weight of the rank move, for other values that are neither 0 nor 1. Particularly interesting probably the values between 0 and 1, because if you reconstruct a tree, you're probably more certain about the topology than about the actual ranking. So if you, to account for that, you can choose a value for a row which is probably closer to 0. So what's the complexity there? To be honest, I don't know. The only thing that I can say for sure is that find path, our polynomial time algorithm, only works for row equals 1. So it does not work for row greater than 1. A counterexample is given here, where we have two caterpillar trees. A1 and A2 build the cherry here, and then A3 and A4 follow, and here A3, A4 the cherry A1 and A2 follow. And then find path would first build a cherry, then do a rank swap, and then resolve the cherry. So we have two NNI moves that way 1, and one rank move that's row. But there's also a path that only consists of caterpillar trees. And for row greater than 1, the path on the top computed by find path is longer than this caterpillar path. So it doesn't, find path does not work for row greater than 1. In a similar way, it does also not work for row smaller than 1. Counterexample is given here, where we have a tree with two cherries, A1, A2, and A3, A4. And here, A3 and A4 are in the middle, and A1 and A2 around them as a caterpillar tree. What find path would do is resolve the cherry and then move A3 down by an NNI move and do further NNI move here to swap A2 and A4. But there is another path where you first swap the ranks of these two cherries and then resolve this cherry and do one further NNI move. And this path is row +2, but if row is smaller than 1, then this path is shorter than the one that find path computes. So find path doesn't work for other values of row. It really just works for row equals 1. And what happens for other values of row, we don't know yet. So there's still a lot of research to do here. What is possible is that there is somehow an interval around 0 where it's NP hard, and then it changes to polynomial, probably stays polynomial, or it changes back to NP hard. I have absolutely no idea. I currently suspect it might be NP hard everywhere but at 1, but I'm not sure. But yeah, definitely interesting topic, especially because the complexity is really depending on this one parameter, which I find quite interesting. But that's not all. I have one generalization of RNNI to show you, and this is generalizing RNNI of 1. So for this unweighted graph, where we can actually compute distances in polynomial time. And this is generalization to discrete time trees. So instead of considered just ranked trees, we now consider trees where we have actually branch lengths, but we want them to be integer valued. So we assign time to the internal nodes, but we only allow them to be integers. So for example, here we have now here an interval where the time difference is 2, and here's 1, and here again there's an h of length 2 and nothing in between. So these trees we call discrete time trees. And we now need a further move because we still only want to allow rank moves if the difference of the ranks between two nodes is 1. But here the rank difference is 2, so we could, for example, not do a rank move here. And also there's no NNI move possible here, and there's nothing we can do about it. So we want another move, and we call this move a length move. And a length move happens basically on 2 intervals, on 2 connected intervals. So we call the difference between 2 nodes here an interval now. And what happens is that we basically just changed the rank of the node in the middle. So we changed the rank of this node, which had rank, the time of it from 4 to 5. By that, we decrease the size of the edge here and increase the size of these 2 edges. But it's basically just changing the time of one node by 1. And this move we now call length move. What you might think about now is that we might get into trouble if we do that, for example, on this edge, and we can increase the length of this edge and increase the time of the root here until infinity if we do lots of rank moves. So we need to introduce a new parameter m, which is the maximum height of a tree, to get a finite graph, because we again want to have this tree graph where the nodes are trees and the edges are different moves, in this case now rank moves, RNNI moves, and length moves. But we want this graph to still be finite, so we need to set a bound on how high the tree is allowed to be. So we call this m. And this gives us this whole new space where we have these different lengths of these intervals. So for example, now we have a length move between this tree here and this tree here, which changes these two intervals here. Then again, we have rank moves between these two dots here and RNNI moves. So now we have three different kinds of moves, and we call this space the space of discrete time trees, DTTM, because it depends on m. We, by the way, always assume that n is fixed the number of leaves. So, and the great thing we can do here is, because it is kind of similar to the RNNI space, we just have this one additional move, but we can actually use our algorithm find path to compute shortest path in the space. The way it works is we need to extend this the trees a bit to make it work. So if we have given two trees, for example, these two guys, where we assume that the maximum height a tree can get is 6, so we have DTT6. We have one where it actually the root reaches 6, here it just has the time 5. But if we want to use find path, we need to add a root on top of this to make sure that they both have the same root, that the root in both trees has the same time. And we not only do that, but we add a new subtree on the right. And we want this to be a caterpillar tree with leaf labels from a n+1, so a6 in this case, to a m, m+1? No, m+2, which is a8. And we add a caterpillar tree, so which is ordered in a way that the lower the label of the leaf is, that the lower the rank of the internal node. So they are ordered the same way here, a6, a7, a8, as they are here. So the cherry here is as well a6 and a7. And we add the internal nodes in a way such that we get a ranking of the tree, so that every possible integer that could be assigned to internal nodes actually has an internal node. So we want to fill this gap here from a1 to a3 with a node which has time a2. And then we as well want to add a node in this gap here between 4 and 6 with time 5. And by this we get a ranked tree where we have every integer between 1 and 7 in this case to appear as the rank of an internal node. And the same way it works here. Here we add a node here with rank 3, sorry, with rank 3, and then on top here, on top of the tree, we need one with rank 6 and then the root with rank 7. And by adding the second subtree, we can now use find path, because now we have two ranked trees as an RNNI space, and now we are in the space RNNI on 8 leaves. And we can use find path to compute shortest paths. And as we know that find path preserves clusters, and we have the cluster property, we know that we can show that actually the shortest path between these two trees will also be a shortest path in the space DTTM. And the length moves that happened before, where you could change the length here, are now correspond to rank moves with the nodes on the right. So that's quite an interesting generalization. And now we can also handle trees with branch lengths that are discrete. So yeah, that's quite cool. And we can use find path for more than just the space of ranked trees RNNI. And with that, I'm actually already, no, I'm not yet at the end. I just wanted to mention again that the shortest path problem here is also solved on polynomial time. But now it depends on m, because we add stuff on the right here to the tree, and that depends. So we add stuff linear and m to it. So the running time of the algorithm find path here would be quadratic in M, which can probably be improved. Yeah, but that's all I want to say. And I'd like to thank my supervisors, Mareike and Greifswald, who also worked on some of the stuff, and my working group. And you for listening.
Okay, thanks for your nice talk, Lena. I think we have some time for questions, and I think there was also some discussion in the chat about, maybe you could tell about the question was, maybe that's solved already, what's the difference between ultrametric and ranked trees? Maybe that became clear when you now also introduced times.
I'm sorry, I can't see the...
Oh, how do you define the ranks? That was basically the question.
So the difference between, so ultrametric basically means that all the leaves are ranked 0. So so we only considered ultrametric trees where, did I say not that we didn't consider? I don't remember. So we always considered ultrametric trees. So we always assumed that all leaves have rank 0, and then the internal nodes have ranks from 1 to n-1. Was that the question? I didn't follow, sorry.
It was my question, essentially. Do you hear me?
Yes.
So I was lost at that point where the definition of the rank was defined. So I was somehow in between these ultrametric things, which gives us a ranked tree. But how do you define a ranked on an arbitrary tree?
So that there are different ways. I mean, so an arbitrary tree can have different rankings possible. So I mean, these two trees, for example, they are the same tree, just the ranking is different, and you can basically choose arbitrarily. The only important thing that we need to keep in mind that the parent of a node needs to have rank bigger than its child.
Okay, so but it's a partial order, not a total order. So I cannot compare the parents of A4 and A5 with A1 and A3.
So this one has rank higher than that. You just...
Okay.
Yeah.
Okay,